Hello friends. So previously we discussed about rectangular components in two dimensions, and also we discussed about how to perform vector addition through rectangular components, and the discussion was limited to two dimensions, x and y axis. So in this video we are going to discuss about rectangular components in three dimensions. Okay, so x, y and z axis. Okay, x, y and z axis. So here the same concept, but it is extended to this extra axis, which is the z axis. So in two dimension what used to happen is that everything was confined to x and y. Okay, x and y, whatever discussion was there, it was limited to x and y. So it was confined to the xy plane. But here when we add another axis, then it becomes three-dimensional. Okay, so what happens is that here if we say that if we try to locate a point, let's say here, and this is the vector, let's call it a vector. So here we will require x, y and z components to identify this point in space, which is the a vector. So this is the tail, this is the head of the vector, and it will be specified by this. This ax I cap, ay j cap, az k cap. So here this az and k cap, they are the extra thing. In two dimension only this much was required, ax I cap, ay j cap. So as we know, I cap is the unit vector in the x direction, j cap is the unit vector along y axis, and k cap is the unit vector along the z axis. Okay, so ax is the x component, ay is the y component, and az is the z component. Okay, now here again the vector is specified by two important parameters. Okay, first is the magnitude, and second is the direction. Okay, in two dimension we used to do theta is equal to tan inverse of ay by ax, that we used to do. Okay, it was very simple and straightforward. That was the approach to find out the direction, and magnitude was simply the a vector magnitude, that was simply root over ax square ay square, simple application of Pythagoras theorem. Here also it is the same. In terms of magnitude we are just extending the same thing, but the direction of this vector in the three-dimensional space is defined by something which is called as the direction cosines of vector. So we'll come to that. First let us see the magnitude. So here you see, first if we take the x and y component, the A vector is AXI cap AYJ cap plus AZ K cap. First let us focus on these two components, AX and AY. The resultant of these two vectors, AXI cap, AYJ cap, that is, let's call it AXY vector, which is confined to the x and y plane, that is equal to AX square plus AY square. So this is limited to the xy plane. Okay, this is limited to the xy plane here. See, this is limited to the xy plane, AXY vector. Now this AXY vector, okay, this AXY vector which is confined in the xy plane, that is perpendicular to the z axis, that is perpendicular to the z axis or the z component, AZ. So the resultant of this AXY vector and this AZ vector, AZK cap, that will give us the final resultant magnitude, that is AXY square plus AZ square. Okay, and AXY square is simply, this is the magnitude, okay, AX square plus AY square whole square plus AZ square, and that is equal to simply this AX square plus AY square plus AZ square. That is the magnitude, final magnitude. So okay, first to understand, the vector is specified by this AXI cap, AYJ cap, AZK cap. So to find out the magnitude, first what we did, we focused only on the x and y components. Okay, only the x and y components. So we found out the resultant of the x and y vectors, y component vectors, AXI cap, AYJ cap. That gave us a vector AXY vector which is confined in the xy plane. Now we know that the xy plane is perpendicular to the z axis. So any vector confined in the xy plane will be perpendicular to the z axis. See this. Now we focused on the z component, AZK cap. So to find out the final magnitude, first what we did, that is the resultant of the final magnitude vector or the final vector A vector is AXY vector plus AZ vector. So in order to find out the resultant of these two, the resultant magnitude of these two, we did this like we did here, AX square AY square, we replace that with this AXY square plus AZ square. AXY square we found out this, that is AXY, AX square plus AY square. When we did the square of the square root, the square root was removed and we got this. The final magnitude is A is equal to AX square plus AY square plus AZ square. So this is the simplified result. Okay, this is the simplified result. The magnitude of A vector is AX square plus AY square plus AZ square, where AX is the x component, AY is the y component, Z is the z component. First we focused on x and y, got the resultant vector in the xy plane, that vector is perpendicular to the z axis or the z component. Then we found out the resultant of this xy resultant, x and y component resultant and the z component, and that got us this result. So the magnitude is done. Now we have to focus on the direction. So as I said, the direction is specified by something which is called as the direction cosines of the vector. Okay. Now suppose the x, y and z axis, okay, the vector which is here present, a vector, it makes an angle alpha with the x axis. Okay, with the x axis, the a vector, it makes an angle alpha. With the y axis, it makes an angle, let's say, beta. And with the z axis, it makes an angle gamma. This. Then the direction cosines of the vector, it is specified as cos alpha, cos beta and cos gamma. Okay, this is the whole concept. Cos alpha is specified as, it is expressed as the x component divided by the magnitude of the vector, which is a. Cos beta is specified as the y component divided by the magnitude a, and cos gamma is specified as the z component divided by the resultant, the magnitude a. This, and these are called as the direction cosines. Okay, so we can also write ax as a cos alpha, ay as a cos beta and az as a cos gamma. Okay, and another important property is that we know that magnitude is ax square plus ay square plus az square. When we square both sides, we have a square is equal to ax square plus ay square plus az square. Now we replace ax, ay and az with these, a cos alpha, a cos beta, a cos gamma. So it will be a cos alpha whole square plus a cos beta whole square plus a cos gamma whole square. So that is equal to a square cos square alpha plus a square cos square beta plus a square cos square gamma. Again, that is equal to, that implies a square is equal to a square into cos square alpha plus cos square beta plus cos square gamma. So a square got cancelled, that implies cos square alpha plus cos square beta plus cos square gamma, that is equal to 1. This is another important property of the direction cosines of the vector. Okay, so these are the basic concepts related to rectangular components in 3 dimensions. Okay, so here an extra axis, z axis, came into play. The vector is specified in terms of the x, y and z components, I cap, j cap and k cap being the unit vectors along the x, y and z axis respectively. Magnitude first taken into consideration the x and y components, which got us a vector, resultant vector in the xy plane, that is perpendicular to the z axis of the z component. and then taking both of them into consideration, we got the final magnitude. Direction specified in terms of the direction cosines depending on the angle which the vector, particular vector, makes with the x, y and z axis, which is alpha, beta and gamma, and the direction cosines cos alpha, cos beta and cos gamma specifies the direction of the vector. And this is the property, important property related to direction cosines. Okay,